week 11. This will be the second week for us to study impulse and momentum. In this week, we learn the theorems of conservation of linear momentum and conservation of angular momentum. Firstly, conservation of linear momentum. Starting from principle of linear momentum. If the sum of all the linear impulses acting on a rigid body or a system of rigid bodies is zero, the linear momentum for a rigid body or a system will be constant or conserved. So this means initial linear momentum L1 should be equal to the final linear momentum L2. This equation is applied about the mass center point G of the rigid body or the system. Next, we introduce conservation of angular momentum for one rigid body. Starting from principle of angular momentum, if the sum of all the angular impulses due to external forces acting on the rigid body is zero about the mass center point G, the angular momentum of the rigid body about point G should be constant. So here, Hg1 should be equal to Hg2. If the sum of all the angular impulses about point A is zero, then the angular momentum of the rigid body about point A is constant. HA1 is equal to HA2. Okay, here you can see the key is a suitable point must be selected when we apply conservation of angular momentum for one rigid body. If the initial condition of a rigid body or a system is known, conservation of momentum, this theory is often used for determining the final linear or angular velocity immediately after an event occurs. In a system consisting of more than one rigid body, if we consider these rigid bodies altogether, when we apply conservation of linear momentum, the mass center point of each rigid body may be used. For conservation of angular impulse and momentum for a system, a same reference point, for example, point O, must be used for every rigid body. The conservation of momentum equations can be used if there exist only non-impulsive forces, or the impulses generated by external forces are small. For some problems, this is the kind of approximation with high enough accuracy. A non-impulsive force causes negligible impulse. Specifically, one small force acts over a very short period of time. An impulsive force means a force that is very large and can generate high impulse, although it acts for a very short period of time. For example, the force from a racket on a tennis ball, or a force between the round stones in curling, or between the balls in snooker. Let's watch two short videos. First one, the force from a racket on a tennis ball. For this tennis ball, it has a weight force. When this racket hits this tennis ball, it will have an impact force from this racket. Comparing to weight force of this tennis ball, this impact force is very high, and this impact force is impulsive force, but the weight force is not. The second video shows the impact force between the round stones.
And back up a bit and maybe buried. The bonus is getting that third yellow. We're not too concerned about it though.
Jake, first.
Do something good.
Whoa. Do something good. Bang, bang. And back up. And back up. Oh, my.
Great call.
Just hit it perfect. Absolutely perfect.
Best kick.
I think the backwards a foot and a half.
Yeah, I know. Yeah.
Please note here, we are talking about very short period of time. For example, from T1 to T2. Impulsive forces occur due to, for example, an explosion or the striking of one rigid body against another one. Non-impulsive forces may include the weight force on a rigid body, the force imparted by a slightly deformed spring with relative small stiffness, or any other forces that is very small compared to other large forces. Impulsive force and non-impulsive force are not absolute concepts. If an object is in static or in a motion, but the velocity is very low, the weight force of this object may be non-impulsive. But if a dropped object hits another object at a reasonable higher speed, the weight force of the dropped object may become impulsive. Okay, now applications of conservation of momentum. The most typical application is ice skating spin. Firstly, let's watch a video, and this video shows a simulation of ice skate spin.
Welcome back. It is another fun Steve
Fun.
Spangler
This is gonna be
science
fun.
morning. Fingers crossed. I'm sure if you didn't see the preview before, I'm going to be spinning on that.
The Olympics are not over in the minds of teachers and parents who are
Right.
using them as a teaching moment, right? So
Okay.
there's a lot of good stuff that's out there. I'll say at the very beginning here that NBC Sports put some great science video up, and we linked all of that together and tried to put some things together. We're going to talk about the spin, all
Okay.
right?
Like
Now, a
you
lot
said.
of people do this demonstration by having people spin in an office chair, all right? But why would you do that?
Ah.
Because you're sitting and that would be safe.
Right.
So here's what you're going to do. You
We're not
are
gonna
going to
do
be on
things
this
safe.
exercise thing. See this little exercise thing here?
Yes.
Has ball bearings. It's like a lazy Susan for a person.
Oh, good.
All right, so now here. All right, good. So now you just stand on this, okay?
I almost fell off of this just
Okay.
trying to stand on it.
You
before.
were so good at this.
Okay.
All right, so now this is all about angular momentum, all right? So before
Yeah.
everybody goes to sleep, here's the deal. You're gonna spin, you're gonna put your arms out like this.
Okay.
So I'm gonna spin you like this.
Oh,
Okay, see?
Oh my
That's good,
gosh.
good. No, it's okay, you're fine.
Yeah,
All right, so
I
now
know.
watch this. So now you're gonna be okay. I'm gonna spin you again, but this time I want you to take your arms that will act as weights. I want you to bring them towards your chest.
Okay.
Okay, so what's gonna happen is you're gonna change the moment of inertia from here to here. Got it?
Okay, got it.
So here we go. You ready? So kind of spin around. Now bring it. Oh, see how great that was? Okay, you're okay. You're okay. Okay. But now, see, isn't that fun? But now if you take your arms and put them back out again, you'll slow down. Okay, so here, try it. Okay, ready?
All right.
So a little spin like this, okay? Arms in, good, arms out. See, now you see
I
how
like
you
arms
control
out.
it? All right.
Arms out's a lot more fun.
But this is a lot more fun, all right? All right, so hang on to these weights,
Okay.
So this is good. All right, so this is good. Now, you're gonna get going a little bit, and then I'm gonna bring you in. Okay,
Okay.
ready? So spin around like this. So we're changing. Okay, stay there, stay there, stay there. Now go in. Whoa! See? Honey, it's just because I'm helping. I know I'm gonna pay for that. All right, so here, hang on here again.
Yes.
See, is that great?
Dizzy, Steve.
No,
I
you're
know about
fine.
this.
Yeah. Wait till you get to do the weather after this.
Yeah,
Okay?
great.
So what's the weather today, Becky? Okay, so watch. You're not gonna go as fast. You're gonna bring him in. Ready? So we're changing the moment of inertia.
Yeah.
Bring it in. Ready? Oh, was that awesome? Oh, you were so good. See, that was perfect. Isn't that great?
That was kind of fun.
All right.
Except
So
for the falling off part.
angular momentum, velocity. So if you change the moment of inertia, you have to spin up to keep
Right.
everything constant. So kind of fun to do. So if you don't have one of these, you try an office chair. But when you graduate to this, I've been busy all weekend long, just working.
Seriously.
Isn't it fun?
In ice skating spin, the friction forces from air and ice are very small, so they can be treated as non-impulsive. The sum of angular impulse should be approximately zero. So conservation of angular momentum can be applied. Okay, let's watch a video.
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular.
In this video, angular momentum is error. In the lecture notes, angular momentum is h.
The best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Next, we use conservation of momentum to solve a few example problems. In the first example problem, and here you can see there is a platform, and this platform can rotate about a fixed axis through its circle center point. And here there is a man. The man and the platform were at rest initially. The platform, its mass is 150 kilo. The man, its mass is 75 kilo. This man leaps off this platform. The velocity at this moment is 1.5 meter per second. And this velocity is the relative velocity of this man to the platform. The task here is to determine the angular velocity of this platform immediately after this man lifts off. This problem looks not very easy, but if we have a top view on this platform and this man, we can treat this problem as a planar rigid body dynamics problem. Okay, we define this problem. We can consider this man and the platform in one system. If we have a top view on this platform and this man, and we define this view is on an XY plane here, then you can see in this plane, in this XY plane, no linear impulses and angular impulses generated by external forces in this plane. The force between this man and the platform should be internal forces. They are not external forces. When we talk about external forces, there should be weight force on this platform and weight force on this man, but they are perpendicular to this XY plane, so it's not necessary to consider them. Two positions. Initial position, state 1, that's immediately before this man leaps. Final position, state 2, that's immediately after this man leaps. And you can see the time interval between this initial position and final position is very, very small. And this time interval cannot be measured. For solving this kind of problem, impulse and momentum, this method is the only choice. Because no linear impulses and angular impulses generated by external forces. For solving this problem, we can apply conservation of momentum. Okay, now the diagram. And that's the top view of this platform and the man. This is XY plane. We can define a coordinate system X, Y, and we can define counterclockwise as the positive rotation direction. And here we let X or Y axis along the line connecting points O and P. We'll be able to simplify our calculation. And here we let X axis along line OP. Okay, we already know the mass of this man, the mass of this platform. Initially, they are at rest, so Vm1 and Vp1 should be 0. Vm1 is the initial velocity of this man. Vp1 means the initial velocity of point P, where this man stands. This point P is on the platform. Omega 1, of course, is 0. The relative velocity of this man to the platform when this man leaps off is 1.5 meters per second. Okay, here we don't know Vm2 and Vp2 and omega 2. We can apply conservation of momentum, and we can apply conservation of linear momentum, and also we can apply conservation of angular momentum. Next, you will see actually only the conservation of angular momentum is useful. The conservation of linear momentum is not useful for solving this problem. Okay, now we will express Vp2 and Vm2 using omega 2. Because finally, we have only one equation. This means we can solve only one unknown parameter. Vm2, Vp2, and omega 2, these three are not independent. And we can actually use any one of these three unknowns to express the other two. Okay, Vp2 is equal to omega 2 times the distance from point O, the rotation center, to point P. By observation, we know this angular velocity immediately after the man leaps off should be clockwise. Then Vp2, a point P on this platform, should be vertical, downward, and this should be negative according to this defined coordinate system. So that's why before 2.4 omega 2, there is a negative sign. Vm2 can be calculated using Vp2 plus the velocity, the relative velocity of this man to the platform. So that's negative 2.4 omega 2 plus 1.5. Next, we calculate the angular momentum in initial position and final position. In the initial position, next we calculate the initial angular momentum and the final angular momentum. Because here it's a system, there are two rigid bodies. For this calculation, a same reference point must be used for calculating the angular momentum of both the man and the platform. And we select the circle center point O for this calculation. So two items, one for the man and another one for the platform. Because initially Z are velocities are 0. So the summation of angular momentum of these two rigid bodies in initial position should be 0. For the final angular momentum, one item is about the man and one item is about the platform. For this platform, its ongoing rotation about a fixed axis through point O. So this will be IO omega 2. Omega 2 clockwise, it should be negative. So here there is a negative sign. The sign of this angular momentum of the platform is equal to the sign of the angular velocity, omega 2. For this man, this calculation you can see is actually the angular momentum of a particle. Okay, we substitute Vm2 from here to here. And finally, we can get the expression of the summation of angular momentum of this system. Initial angular momentum and final angular momentum, they are equal because of conservation of momentum. So omega 2 can be worked out. And here, this omega 2, you can see it's positive. That means in the diagram, they assumed or they observed the direction of this angular velocity omega 2 is correct. It should be clockwise as indicated here. According to the defined coordinate system, this omega 2 should be negative. Okay, now the second example problem. In this problem here, you can see two rigid bodies. One is a slant rod, and this slant rod can rotate about a fixed axis through point O. Initially, this slant rod was at rest. A bullet is fired into this rod. Its velocity is 500 meters per second. This bullet will become embedded in this rod. Okay, now the task is to determine the angular velocity of this rod immediately after this bullet becomes embedded into this rod. Okay, we still consider these two rigid bodies altogether in a system. Then the impact force between this bullet and the slant rod will be a pair of internal forces, and the impulses generated by this a pair of internal forces should have same magnitude but opposite directions. So it's not necessary to consider the internal impulses. Okay, define this problem. We know we consider this bullet and the rod in one system, so the impact forces between them are internal and they can be eliminated. Two positions or two states. One is immediately before impact happens. State 2 will be immediately after impact happens. Again, between this state 1 and state 2, the time interval is very, very small. It cannot be measured. So, for solving this problem, impulse and momentum method should be the only choice. Comparing to the impact force, all other external forces can be considered as non-impulsive. And here there is a diagram. This is called the impulse momentum diagram. Here is initial momentum diagram. The slant rod and the bullet. The bullet, its linear momentum is mb/vb1. Here, this one, a final momentum diagram. Immediately after the impact, this slant rod gets a velocity, and here this is the bullet. Its velocity will be as same as the velocity of this slant rod because this bullet is embedded into the rod. The slant rod gets a angular velocity omega 2. In the middle, this is an impulse diagram, and here we can indicate the impulse generated by WG, the weight force of the slant rod, WB, the weight force of the bullet, and the reaction force at this fixed axis is 0.0, OX and OY. Impulse, WG delta T, WB delta T, and OY dt. These three are balanced. About point O, the moment arms of OX, OY, WG, and WB, they are all 0. So this means they don't generate any angular impulse. And here you can see, when I express the impulse generated by WG and WB, I use their magnitude times delta T directly because WG and WB, they are constants. For reaction force OX, OY, I use integral because the reaction force at point O in the time interval when the impact happens, the reaction force should be a variable but not a constant. Okay, for solving this problem, we have to use conservation of momentum. We already know the mass of this rod, the mass of this bullet. We know VB1, VG1, omega 1. For VB1, that's 400 meters per second. But for VG1 and omega 1, because the slant rod was at rest initially, so the velocities must be 0. Okay, we don't know VB2, VG2, and omega 2. And again, you know, these three unknown parameters, they are not independent. And we actually can use any one of them to express the other two. The mass of this bullet is only 4 grams, and the mass of the rod is 5 kilo. So this means the mass of this bullet is significantly less than the mass of the rod. So when we calculate the MMI of this slant rod after the bullet becomes embedded into the rod, we actually can neglect the influence of the mass of this bullet. It's too small. Okay, for solving this problem, only the conservation of angular momentum is useful. We calculate the initial angular momentum of this system. One item for the bullet, another item for the slant rod. For the slant rod, its velocity in state 1 is 0. For the bullet, this calculation again is actually the calculation of angular momentum of a particle. The distance from point O to the linear momentum MBVB1 can be calculated using 0.75 times cosine 30 degrees. Final angular momentum. One for the bullet, one for the slant rod. Okay, finally, only one unknown parameter, omega 2. Omega 2 can be worked out because of conservation of angular momentum So the summation of angular momentum in state 1 should be equal to the summation of angular momentum in state 2. Omega 2 is 0.623 radians per second. Okay, this calculation result is positive. And that means the indicated or observed direction of omega 2 in this diagram should be correct. Should be counterclockwise according to this defined coordinate system. It should be positive. When solving this problem, you can see we must select point O to apply the conservation of angular momentum. Okay, example problem 3. In this problem here, there is a wheel. We know its mass, we know its mass moment of initial about its mass center point G. Assume this wheel does not slip when it's rolling on the ground. No rebound when this wheel hits the obstruction at point A. The task here is to determine the minimum velocity Vg it must have to just roll over the obstruction. This is a difficult problem. For this kind of problem, there is a process. We must clearly define the states. So the first question here is, for this kind of problem, what states can be defined? Okay, firstly, let's see a similar problem. We will define the states for solving this kind of problem. In this problem here, there is a slender bar. It's falling down, and it will contact this corner point O, and after that it becomes adhered to this point O, then continue falling down. Let's see this animation again. Okay, here we already know its initial velocity v1, and the target here is to determine the angular speed after this slant bar has rotated 60 degrees from the horizontal position. Okay, in this whole process, actually we can define 4 states. The first state, initial state, here at this moment, the slant bar is undergoing translation. Its velocity is v1. In the second state, this bar immediately before this slant bar hits this corner point O, it's still undergoing a translation, but the velocity becomes v2. v2 must be larger than v1. Why? Because the gravitational acceleration. State 3, immediately after this slant bar hits this corner point O. Because this bar becomes adhered to the obstruction at point O. So immediately after this impact, the bar will be undergoing rotation about a fixed axis through point O. State 4, when this bar has rotated 60 degrees from the horizontal position. So totally 4 states. Okay, we come back to this problem. Let's see what states or positions we need to define for solving this problem. It is not mentioned in this problem, but we can reasonably assume the acceleration on the wheel is 0 before it hits the obstruction at point A. So the first state, state 1, can be the instant immediately before the wheel hits the obstruction. The second state, state 2, can be the instant immediately after the wheel hits the obstruction. After hitting the obstruction, the wheel will be rolling over the obstruction and its position will become higher. It means the gravitational potential energy of this wheel will be increasing while its kinetic energy will be consumed. So the velocity of the wheel will be decreasing before the wheel reaches its highest position. This problem asks us to determine the minimum initial velocity the wheel must have to just roll over the obstruction. This means when the wheel is at its highest position, its velocity should be 0. Now, the instant when the wheel is at its highest position will be the final state, state 3, when solving this problem. Okay, now let's define this problem. Because of no slipping or rebound, we know the wheel undergoes rolling motion without slipping before it hits the obstruction. So that is general plane motion. After the wheel hits the obstruction, the motion should be a rotation about an axis through point A. We have already defined the 3 states. State 1 is immediately before hitting, state 2 immediately after hitting. So, you know, the time interval between state 1 and state 2 must be very, very small. It cannot be easily measured. So, for this process from state 1 to state 2. Impulse and momentum method should be the only choice. When the wheel rolls over the obstruction, that process, that problem, is a problem that can be solved using equation of motion plus kinematics. But we studied work and energy method in week 9, so we know work and energy method should be more direct. For state 3, the velocity of the wheel should be 0 based on our analysis just now. Okay, now we can have our diagrams. Here, this one is impulse momentum diagram, and this one initial momentum diagram, and this one the momentum diagram in state 2. In the middle, this is the impulse diagram, and here you can see the impulse generated by weight force of this wheel, by reaction force Mb, by friction force Fb, and by the impact force Fa. Fa should be a variable, so to express its impulse, we use integral of Fa with respect to time. From state 2 to state 3, this is a problem that can be solved using work and energy method. In this process, you can see only the weight force W of this wheel can do work. And we know weight force is a conservative force. So this means to solve the problem from state 2 to state 3, we should be able to use conservation of energy. And we need a datum. And here, I put my datum here, going through the mass center point G when this wheel is in state 2. We have already known the mass of this wheel, 10 kilo mmi of this wheel about its mass center point G. And we know in state 3, the velocity of this wheel is 0, Vg3 0, omega 3 0. We don't know Vg1 omega 1, we don't know Vg2 omega 2. But you know, Vg1 and omega 1, these two can be related to each other. And Vg2 and omega 2 should be able to be related to each other using kinematics. So how to solve this problem? For the process from state 2 to state 3, we know we can solve using conservation of energy. But how about the problem from state 1 to state 2? Okay, have a look this impulse diagram. Comparing to impact force Fa, all other external forces, the weight force, friction force, or reaction force Mb, they are all non-impulsive. So even we concede the impulse generated by W and Mb, you can see these two, they are impulses, can be balanced to each other. So this means if we select point A to calculate the angular impulse, because the moment arm of Fa, the only impulsive force here, the moment arm of Fa is 0. So the angular momentum immediately before this wheel hits the obstruction at point A, and after that, the angular momentum should be a constant. So this means we can apply conservation of angular momentum about point A. Okay, now let's have a look the calculation. In the first step, we apply conservation of angular momentum for the process from state 1 to state 2. In state 1, point B is the IC point. The distance from G to A can be easily calculated, so we can express Vg1 using omega 1. In state 2, point A is the rotation center point. The distance from G to A is 0.2. So we can express Vg2 using omega 2. Now calculate the angular momentum of this wheel in state 1 and in state 2, and substitute the expression of Vg1 and Vg2 into these two equations. And finally, we can get the relationship between Vg2 and Vg1. So now we have relate Vg2 and Vg1. Now, in the process from state 2 to state 3, and that's a problem that can be solved using conservation of energy. We calculate kinetic energy of this wheel in state 2 the kinetic energy of this wheel in state 3. In state 3, because the velocity of this wheel is 0, so kinetic energy in state 3 should be 0. We calculate the potential energy of this wheel in state 2 because the datum is set along the mass center point G when the wheel in state 2. So Y2 should be 0. So this means the potential energy in state 2 should be 0. And we can get the expression of potential energy of this wheel in state 3. Because of conservation of energy, so T2 plus V2 should be equal to T3 plus V3. Okay, now here we can work out Vg2. And previously we have already worked out the relationship between Vg2 and Vg1. So finally, we can find Vg1. This is the minimum initial velocity of this wheel required for the wheel to just roll over the obstruction.